Hello?
Hey Kara, how did you do on the last test?
I mean, I guess I did alright. It wasn't the A I was hoping for, but a B isn't that bad. You know, learning about the senses has really got me thinking. 2020 is the year of revolution, and it would be foolish to assume humans are the only ones revolting.
I am not following.
I mean, take a moment to think. When was the last time you stopped and showed your appreciation for those responsible for that gratification? What if, philosophically speaking, the coronavirus is the cells revolting, specifically those found in the face, vision, and taste?
Smelling and hearing?
Yeah, you get it. I'm talking a senses revolution.
And if we do nothing, philosophically speaking, of course, if credit is not given where credit is due, perhaps soon this virus will take over and no revolution will spread to all the senses, not just scent and taste.
It's time we be their voice.
We will start the senses revolution.
Let's see what we got here. We got the instruction manual. Let's see here, we got all the screws, the legs, all right here. Wow, they make this easy to follow. So easy to read. Man, this company's great.
Hey, dude, that's insulting.
I don't understand. Insulting?
I mean, have you even considered how your vision cells feel? I'm disappointed. Alright, you know what? I'm gonna explain this to you. Actually, you know what? I need to take and get some visualization. Your cells could help you read and visualize what I'm trying to teach you. So just give me a second. Alright, now that we finally got that finished, let's get started. Alright, here we have your face. Here we have your eye. You might have seen a diagram like this before. We're only focusing on certain parts, particularly the retina, which is an extension of the optic nerve, which also just happens to have the fovea on it, right there, where the image that you're looking at is actually reflected onto. Most of the work has the majority of your photoreceptor cells. Now, the lens is also important, but really we're not going to get into those. We're actually going to go into the cells themselves. Let's hop over here. Okay. Now, you may know that cells have different functions and stuff. In terms of the senses, eyes are very unique because instead of creating a normal action potential where it goes from polarized to depolarized, this goes from depolarized to hyperpolarized. Eye cells are awesome that way. They're unique. They're hipsters. All right. In order for you to see and understand what you are reading, well, it takes 3 types of cells. Well, 3 main players. There's others, but we're focusing on 3. Now, these 3 are photoreceptor cells, bipolar cells, and ganglion cells. Each play a big role, and it gets even more complicated than that because, you see, photoreceptor cells have 2 types. Yeah, they have the rod and the cone. Rods only collect a little bit of color, where cones collect a lot of color.
I think I'm following.
So rods you use more at night, where cones you use more during the day, which is why you can see color. Okay, I see that we're losing you. So we're just gonna just forget about that. We're just gonna focus on the steps and everything that your cells do. Just brief and easy, understandable steps. All right, we're heading back over here. All right, where are we? All right, so photoreceptor cells, those gather the light. They gather it up and send it to your bipolar cells through the use of a graded potential. Now that graded potential sends that information to bipolar cells, as we just said. Those bipolar cells then take and process it and, well, pretty much do stuff like contrast, and they also take and help you with peripheral vision. Many more things. But again, just the basic steps. Bipolar cells do all of that work, then create yet another graded potential that sends it to the ganglion cells. Ganglion cells, being much fewer than the, say, photoreceptor cells or even the bipolar cells, have a big responsibility of taking all the information that hundreds of these cells send them to the brain. So they take and create an action potential, different from a graded potential, and create that action potential, which then sends it to the optic nerve and is then sent to your brain so that you can read that in perfect clarity. You won't be able to do nothing without those eye cells, so show some stinking appreciation.
Well, I guess I just never thought of it that way. I'm sorry, Vision, if I insulted you. I didn't mean nothing by it. I appreciate all the work you do for me. And I want to look you in the nuclei and really, really tell you I appreciate you and I support your revolution.
Hey guys, so as you know, I am preparing for my senior recital, which is coming up, and there is this French piece that I love so much, and I was wondering if you guys would take a listen and tell me what you think about it. Yeah? Yeah? Cool. Yeah. Awesome. So, here we go.
Wow, Paul, that sounds so great!
Really, Maddox, you think so?
Yeah!
Oh my gosh, well, don't give me all the credit. Your ears also deserve some awesome credit, because if you didn't have your ears, then you wouldn't be able to process the sound. So, can I just tell you a little bit about how your ears work?
Yeah.
Awesome. So basically, when I sing, my voice produces sound waves. And so those sound waves go into your ears, and that's how we process, and then that's where sound processing begins. So this is how it works. So the sound waves go from here and to the tympanic membrane, and they shake the tympanic membrane, and then, come here, Brendan, and then after the sound waves shake the tympanic membrane causes the ear bones, they cause the ear bones to shake too. Then after that, the ear bones are shaking and they amplify sound on the oval window. And so you're the oval window. So once the oval window starts shaking, then it compresses fluid inside of the cochlea. And so this is kind of what's happening, compressing fluid. Okay, so after the oval window compresses fluid, then the basilar membrane eventually vibrates and causes the fluid to deflect these things called hair cells in our ears. So hair cells basically tell our brain what kind of sound we're hearing, what frequency of sound we're hearing, and how loud the sound is. So this is how it works. You're a hair cell, and when the fluid moves, you move, which is called deflection. So when you move to the right, then it tells our neurons to depolarize, and when you move to the left, it causes our neurons to hyperpolarize. And that is how our brain knows how to process the sound, what kind of sound it is, and all those things. And so just a couple things to know about when the hair cells are moving. The more they move, so if you move this much, you're not going to have as high of an amplitude or as many action potentials. But if you move this much, you're going to have so many more action potentials because there's a higher amplitude because you moved more, right? right?
Yeah.
So, another important feature to note is that the cochlear hair cells have specific locations for different frequencies. And so, a hair cell that is over here moving is gonna register a different sound than a hair cell over here that's moving as well. So, for example, in one area you can hear high pitches like high pitches. And then in another area, you can hear low pitches.
And normal pitches.
And normal pitches too. Another thing our ears are great for is determining our body's equilibrium. So we have these things in our ears called the semicircular canals. And in these canals are stereocilia hair cells and fluid. So depending on which way our body is moving, the fluid can move on 3 different axes. And this fluid will deflect the hair cells inside of the canals, and it tells our brain which direction our head is in or our body is in. And so when our hair cells move to the right, then it tells our neurons to depolarize. And when our hair cells move to the left, it tells our neurons to hyperpolarize. And that is how our body determines our equilibrium. Hey Brendan, your cookies are ready.
Yes.
Ooh, it smells great. Yeah? Oh, good. I'm glad you think so. You want to know an interesting fact?
Sure.
So there are only 1,000 olfactory receptor genes in our whole entire genome. Isn't that crazy?
Mm-hmm.
Do you know what that means?
No.
Okay, so basically olfaction is the process of smelling and like processing how we smell things. So olfactory receptor genes are what cause us to smell. So it's really interesting because we only have 1,000 of these genes in all of our DNA, but don't you think there are more than 1,000 different smells in the world?
Yep. That could be.
Yeah. So it's interesting because this works through co-activation of receptors. So receptor 1 and receptor 800 can work together to smell a whole new smell. So we can smell like 10,000 different odors with only our 1,000 receptor genes. That's so crazy.
Mm-hmm.
So an interesting fact again is that our olfactory neurons are actually the shape of like squids. So the way that our smell works is that these little olfactory bubbles come from the cookie into our noses, and the smell particles that come from the cookie, they dissolve in our extracellular fluid, and that is how our neurons are able to accept them. So you want to see the process of how this happens?
Sure.
Okay, awesome. So basically this is what happens. A molecule, one of the molecules from the cookie come and dissolve into the fluid, which is out here, and then this is inside of the cell. So here's the fluid, and it comes into a GPCR, which is a G protein coupled receptor, which activates this G protein, and the alpha subunit goes and activates adenylyl cyclase, which activates a second messenger, or CAMP. So CAMP comes to this cation channel, and it activates it so that way sodium and calcium are able to enter the cell. So these are 2 positively charged ions. So now we're increasing the voltage potential and bringing it towards 0. So in addition, calcium is going to go to this ion channel and release chlorine out of the cell. So we're pulling positive charges inside of the cell, and we're taking negative charges outside of the cell. And so this is causing a depolarization, which is how our brains process the smell, or at least begin to process the smell. And this is called a metabotrophic pathway, because we're using a G protein coupled receptor. And that's just a small part of olfaction, but it is so awesome and so crazy.
Such a nice day out. Car! From another mister. Oh, and there she goes. Hey. What? You okay down there, girl?
What are you doing here, Hippie Joe?
Yeah, no. Your pops invited me over. He said you've been doing some sort of revolution and I should come check it out. Yeah, you know those cookies you baked yesterday? Oh man, they so good. I had to bring some over to Hippie Joe. You know how he likes your cooking. And he told me, yeah, you go tell the story, Hippie Joe. He does it better. Yeah, he took and brought over some of them there cookies you made, and I told him that, you know, these cookies are the reason that I love to eat. And he said you got something to say about that, something about the taste buds and all senses, you know.
Uh-huh. Okay, so you want to learn about the sense of taste. Okay, we can do that. Alright, so we're going to have to keep it short because I have to get ready for work and I'm soaked. So, so we'll take this flower to explain it. So, this, we're going to just say is your tongue, okay? And on your tongue, you have what's called taste pores, which we'll say right here is your taste pore. Inside the taste pore, you'll find multiple different cells responsible for different tastes. One for salt, one for sugar, which is like sweet flavors, one for bitter and sour. They're all inside one taste pore. Now, backtrack a little bit. Those taste cells, they're taste buds, and they take, and the way that they work is they each individually have different gates and channels that let in various particles and ions. Like, for instance, salt, the taste of salt. That's thanks to a sodium channel. Sodium comes in, creates an action potential, leads you to taste salts. Now, all these taste buds are all linked to one neural transmitter, or nerve fiber, should I say. And that takes and goes, transmits all that information that these taste buds here are gathering up to your brain. And that's just in a brief nutshell how the taste buds take and allow you to enjoy the food, and actually the reason you enjoy eating, Hippie Joe. Yeah. So be sure to appreciate those taste buds because they actually do a whole lot more work than what I just explained, but again, have to keep it short.
Well, I think I understand where you going, man. There got to be some love for all, yo. And not sharing that appreciation with them taste buds, I understand why they be going on strike with that coronavirus and all. You bring up some mighty fine points.
We're the voices of the senses revolution.
We are the voices of the senses revolution. We're the voices for the senses revolution.
We are the voices of the senses revolution.